Hey guys, welcome back to some of our last stuff here in the acid-base unit. We got 3 things left to do, and this is one of them, so we're almost there. Today we're going to be talking about Ka and acid strength. Let me get my fancy pen out. It looks a little bit nicer. There we go. All right, so little review here. When an acid is added to water, it dissociates. We know this, right? You put it in water, splits apart into usually H plus and something else. This dissociation is an equilibrium. Things can go back and forth. So for example, if you're looking at hydrochloric acid here, put it in water, you get some chloride ions, and you get some hydronium ions. And that chlorine and hydronium could recombine and go back the other way. It goes both ways. Now, because it's an equilibrium, you could, of course, write an equilibrium expression for this. Now, this would be hydrochloric acid is a gas, water is a liquid, and these ones would be aqueous because they are dissolved. But yeah, you could write an equilibrium expression. Product, which are the chloride and the hydronium, over reactants, which in this case would be whatever the hydrochloric gas concentration is. We're not going to include water because, of course, it's a pure liquid. There you go. Easy peasy. We've done tons of this stuff, right? Now, here's the cool part. When we talk specifically about acids, we rename that equilibrium constant, which is usually Kc. That's not what we call it for acids, though. We call it Ka, because it's the constant for acids. Even give it a different name. We call it the dissociation constant, because that's really what it is. It's how much of the acid is going to dissociate. And you can use the exact same reasoning for a base, but then you call it Kb. Get it? Ka for acid, Kb for base, pretty easy to remember. And then Kc for everything else, ABC. So here's an example here. So I got ammonia, I'm putting it in water. I'm going to end up with the ammonium ion and some hydroxide. And so we're going to set up Kb the same way we normally would. Concentration of products over my concentration of reactants. I think this is aqueous liquid. And these are ions, so of course they're definitely aqueous. There we go. And yeah, water's a liquid, so you don't include it. So there would be our Kb. I know it's a Kb because I'm dealing with a base. I'm dealing with ammonia. So all right, cool. I've changed the name from Kc to Kb or Ka. What's the point, right? The Ka or Kb value actually tells us how much of a substance will dissociate, which means it's a direct measure of how strong an acid or base is, right? Strength depends on how much it dissociates. If it's almost completely dissociated, we say it's really strong. If not much is dissociated, we say it's weak. And so Ka then tells us how much it's dissociating. If it's a really, really big Ka value, you know it's a strong acid. If it's a really small Ka value, probably a weak acid. And same thing for bases. So for strong acids and bases, we know that the starting acid base almost completely dissociates. I mean, a lot of things just say completely dissociates because it's pretty darn close, which means whatever concentration is left is very small. Whatever's on the bottom is going to be a tiny number, like 10 to the negative 20 or something crazy small like that, which if you divide by something really small, you get an extremely large Ka value. So for your strong acids and bases, sometimes they'll even just write that. Like, what is the Ka? Extremely large. It's so big, it's like almost immeasurable. It's basically saying it pretty much completely dissociates. If you have an acid or base, however, that doesn't completely dissociate, well, we call those weak acids. If you want to compare some of them, how weak is, acetic acid compared to hydrogen peroxide? You want to figure that out? You use Ka. You can look at the Ka value and see which one's stronger or which one's weaker. So let's look at a couple of examples here. First one, we had a 0.75 molar HC2H3O2. Oh, that looks awful without subscripts. I mean, to be fair, acetic acid looks awful even with subscripts, but it's a little neater. There we go. So that's acetic acid. It is a weak acid. You probably know this because you drink it on the regular. It's vinegar. So you got 0.75 molar acetic acid solution. And it's got hydronium ion concentration of 3.6 times 10 to the negative 3. What's Ka going to be? All right, well, here's my acetic acid. And I shouldn't say this is vinegar. Vinegar is a 5% solution of acetic acid. Don't drink pure acetic acid. You'll have a bad day. And this is going to dissociate in water. It says this is a solution, so this is being dissolved in water, I would guess. That's a pure liquid. It's going to give me hydronium ions plus what? Well, I've basically just... The reason they write acetic acid like this, and it looks like a bit of a mess, is because it shows you the H in front that's going to disappear. So basically I write this exact same thing again, but without the H on it, because the H is gone to make the hydronium ion. So what I actually have as an ion is the acetate ion, C2H3O2 minus. And this is nice and easy because it's all 1-to-1 mole ratio stuff. So sweet. Start with balanced equation. Now again, we're looking at an equilibrium. So the easiest way to do this is use a nice chart. I've got my acetic acid. I've got my hydronium ion, and I've got my acetate. I'll put a little minus by it so I remember that's the ion. All right. So what do we know here? A 0.75 molar solution of acetic acid has a hydronium concentration of that. Okay, so initially, acetic acid was at 0.75 molar. It changed by some amount. And I know I would have started with none of these ions. I would have gained some amount of them. And I know at equilibrium what the hydronium is. It's 3.6 times 10 to the negative 3. All right, so if I have 0 and I add something to it to get 3.6 times negative 3, what is x going to be? Well, x has to be just 3.6 times 10 to the negative 3. So what is Ka? I'll do this in a different color because it's getting a little crowded here. It's going to be 3.6 times 10 to the negative 3 times, well, this is also going to have to be 3.6 times 10 to the negative 3 because they're both 0 plus x, right? So I'm just going to write this, instead of doing 3.6 times 10 to the negative 3 times 3.6 times 10 to the negative 3, I'm just going to square it. Over, what is 0.75 minus that? 0.75 minus, 3.6 times 10 to the power negative 3. All right, so instead of 0.75, I've got 0.7464. And you can see, with this number being so small, I could almost ignore the minus x. Remember that trick? I'm getting pretty close. Usually we were saying it has to be a 10 to the negative 4 to ignore it, and you can see why here. I'm accurate. If I were to go to 2 decimals, I'd still be accurate. If I go to 3, then I start to slip a little bit. So I'm real close to being able to ignore it, but I mean, there's no skin off my back. Let's just keep it in here. So 3.6, we'll just calculate this now. 3.6 times 10 to the power negative 3 squared. I wish I had more space. I'll put the answer down here. 1.296 times 10 to the negative 5 divided by 0.7464 divided by 0.7464 equals 1.74 times 10 to the negative 5. There. So that's what it's telling me the Ka for acetic acid is. And if you actually look on that acid strength table I gave you guys, it shows you all the acids in one column. It shows you their their reactions in the middle column. And on the end, it actually tells you Ka. And so you can actually check your work on this one. If you go and look at the Ka value of acetic acid, where's acetic acid on here? I'm halfway down, just under the halfway point. It tells me the calculated kind of Ka is supposed to be 1.8 times 10 to the negative 5. Look at that. We are pretty much identical. So that's a good sign that we did our work right. Let's go back to my black marker here. So that is calculating a Ka if you were to only know how much acid there was. So if you needed to find the Ka for, let's say you invented some fancy new acid, you would throw it in water. You would use probably some kind of like pH meter to calculate this number. And once you know it, you could do this to find what your actual Ka is. How strong or how weak is your acid? All right. Now let's flip it. Let's do it the other way. I need you to find the hydronium ion and find the pH. If all you know is 1.5 molar of an acid, and in this case, it's hydrogen peroxide. So at face value, it looks like I'm missing some information here, right? I only know 1.50 molars. I can't use an ice chart with this because I don't have any equilibrium numbers, or I mean, I could plug it all in, but I'm going to end up doing something like this is not going to work very well. So here's the trick. You use that chart I gave you. That chart tells us a bunch of stuff. If I look up hydrogen peroxide, not only will it tell me the Ka, it also tells me the balanced equation. So a little shortcut there. So the hydrogen peroxide balanced equation, H2O2 plus water gives me, and one of these hydrogens travels over there to give me my H3O plus. And what's left? Well, HO2 minus. Not H2O, HO2 minus. That's a peroxide minus its hydrogen. HO2 minus. So that's kind of a weird one. But good news is it's all 1 to 1 to 1 to 1 ratios, which is really good. Now I can do my ice chart. So I've got H2O2, H3O plus, HO2 minus. So all I know is that initially I had 1.50 molar peroxide. What is the change? No idea. I didn't start with any of this. We're going to figure out what the change is. Now, I don't know any of my equilibrium values. So this is going to be one of those where you got to actually set it up, and you're going to need to know Ka to do this. Well, let's finish the chart, and then I'll tell you where to get Ka from. This will be 1.5 minus x, x, x. So Ka equals hydronium times whatever the heck this one's called. So it'll be an x squared, x times x, over 1.5 minus x. All right. So this is going to be a quadratic. At least it looks like that. And so what's Ka going to be? Well, you look it up out of that acid strength chart, right? You look up the hydrogen peroxide on that table I gave you in those colored sheets. You go to the very end. I think hydrogen peroxide is like 5 up from the bottom or 6 up from the bottom. And it tells me 2.4 times 10 to the negative 12. So this is a very small Ka. This is a very weak acid, which makes things for us real easy now. Never, ever forget that trick. Never forget that you can ignore x if your Ka is way smaller than whatever you're subtracting it from. So 10 to the negative 12, very, very little is going to dissociate, which means whatever that change is, if I subtract it from 1.5, it's not going to make a difference. I can ignore x, and that makes my life so much simpler, because now all I have to do is take 2.4 times 10 to the negative 12, times it by 1.5. 3.6 times 10 to the negative 12 equals x squared. I square root it. Gives me my x value. 1.897 ... times 10 to the negative 6. And that is my equilibrium concentration of H3O plus. So this is my H3O plus concentration. Sweet, are we done? No, I also have to find pH. So if you guys remember, pH is the negative log of H3O plus. So I didn't even take this number out of my calculator. I left it in there. You could round it probably to 3 decimals if you wanted to be accurate, but I'm just going to leave the whole thing in my calculator. It'll give me a better answer anyways. I'm going to hit the log button. I'm going to flip the sign on it. So this acid has a pH. We know it's an acid, so pH has got to be below 7, right? And it's a weak acid, so it shouldn't be too low. Turns out it's a pH of 5.72, which totally makes sense. A weak acid would be sitting... Who's that? Oh, Mr. Bergen. All right, I'm good. Want to make sure I didn't have a call. Okay, so yeah, pH works. This makes sense. This answer is totally on board with what it should be. Below 7 because it's an acid, but not like a 1 or a 2 or a 3 because it's a weak acid. And so that's how you solve this kind of problem. You set up an ice chart still, you pull Ka right off your colored table. If it's a weak acid, there is a very, very, very good chance you can ignore X, because weak acids tend to have very small Kas. And then you're off to the races and good to go. So that pretty much summarizes our Ka and our acid strength stuff. So thanks for watching, and I'll catch you guys later.